So good evening. This is the course on stochastic processes. This is the class 3 of stochastic processes. So, okay, let me just do a quick recap on. You're able to see the screen, right?
Yeah, yes.
Yeah. So in the first class, I gave a brief topic-wise discussion on what we'll go into. The first class was an introduction. Then three to four classes will be on review of probability. Then 2 to 3 classes on Poisson process, 2 to 3 classes on renewal theory, 3 to 4 classes on Markov chains, continuous Markov chain. So this is discrete time Markov chain, continuous time Markov chain. So total of 8 classes on Markov chains. So this will cover most of the topics that we will. Markov chains will be covered most of the classes that will be going on. And finally, we'll do some interesting examples on random walks. Random walks come up in various other places also. Like these all Poisson, Markov chains and all. Random walks come up there also, but we'll separately see random walks differently. Okay, so and also in the first lecture, I um, talked about probability space. Probability space is basically a triplet of three things. So first you have a sample space. So sample space is a set of all possible outcomes of a random experiment. So now, for example, if you take a coin toss, if you take a coin toss, then the outcomes of that experiment is either head or tail. So the set containing head and tail is the sample space for a coin toss. Similarly, if you throw a die, you get 1, 2, 3, 4, 5, 6. Those constitute as a sample space. Now, events. Events are subsets of the sample space in which the experimenter who is experimenting is interested in. Like he wants to know something about some event. Suppose when he throws a die, he's interested in knowing if odd number, uh, what is the probability of getting an odd number. So getting an odd number throwing a die is an event. It's not an outcome because the outcome is it could be 2, it could be 3, it could be 5, anything it could be. But um, an event is a subset of the sample space. That's why we need to uh, define an event separately. So out of those three things that define a probability space, one is the sample space, which contains the outcome. The other is the event space, which contains the events. Events are subsets of sample spaces. Now, for two coin tosses, the sample space is head, head, tail, tail, head, tail, tail. Now, suppose you are interested in the event that the head occurs first. Then you denote the event as a set A, which you're interested in, and you take the outcomes and form a set of it. So head, head, and head, tail is a subset of the sample space which you're interested in. Now, uh, the space of events is actually a set of sets, but you don't call them a set of sets, you call them as a collection of sets. So collection of sets, they need to have a proper structure before you can define probability on it. So what structure do you want is, so if you're interested in event A, that means you know the probability, you want to know the probability of event A or expectation given event or some um, measure on or some metric on A, then you need to also know some you need to know what is the probability of A complement. Similarly, if you know about events A and B, you need to know about what happens the union of A and B or the intersection of A and B. And then you need to know what happens to the certain event. The certain event should be there in this. So using these three, we define a structure on the collection of sets. So now event space, okay, this is not event space. So a collection of sets is known as algebra of the sample space if the null sets belongs to the collection. And if A belongs to the collection, then A complement belongs to the collection. If A and B belongs to the collection, then A union B belongs to the collection. So this is closure under finite union. Only you can union finite amount of terms. So now the problem with this is you miss. Ashok, could you mute yourself? Thanks. So yeah, if you have a doubt, you can unmute yourself and ask anything. No problem. So tossing a coin until the first head appears. So now you have countably infinite sequence of um, sample space. Here, now suppose you're interested in an event where head was seen in an even number of trials. So this is also a countably infinite sequence. Now, this to 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 generate this, you need the union of infinitely many events. But uh, the algebra set is defined only on finite unions. So you need to extend it to infinite unions. So there you define sigma algebra. So now collection of the subsets of sample space is a sigma algebra if the first one remains same, null set belongs to the sigma algebra. The second also remains same, closed under complements. The third one is modified, now countable unions. So it's not just finite unions, it's countably infinite unions also. So yeah, these are the two things of the probability space. The first one being the sample space and the next one being the event space. Then you define the probability measure. The probability measure is basically it's a function. So you take an event and you assign a number between 0 and 1 to it and say that okay, the probability of this event happening is 0 or 1. So some axioms of probability are probability of null set is 0, or this is also known as impossible event. The probability of an impossible event is 0. Uh, no, this is not impossible. This probability of null set is 0. Probability of the certain event is 1. If you have a sequence of countably infinite events, they belong to the event space, then such that these events are disjoint. So when the events are disjoint, what does it mean? It means two things. So one is the intersection is null set, and okay, I forgot to write here. Union I equal to 1 to infinity ai is equal to the certain space. Okay, this is the partition. Okay, this is no need here. Disjoint means the intersection is null set for all I not equal to 0. When you have disjoint events, then the probability of the disjoint events is just the sum. This property of the probability function is known as countable additivity. So now you have three things that you have defined to have the probability space. The first is a sample space. The second is an event space. The third is a probability measure on it. Then we discuss some properties of the probability function for the first class. And then in the second class, we discussed one property of probability measure, probability function, which was the continuity property of the probability measure. This was a long topic because I need to introduce what limit of sets mean. So since events are sets, which are subsets of sample spaces. So yeah, so I'll go to the final continuity of probability means, yeah. So if you have a sequence of events and the limit exists, limit of all those sequence of events is a, then you can interchange the limit with the probability function. That is what it means when you say continuity. So this is equal to probability of limit n tends to infinity a. So you can interchange the limit and the probability measure. This is the proof that we did in the continuity part. Yeah, this is all the proof. Then we saw Borel-Cantor lemma. Borel-Cantor lemma will actually use it later when we solve some problems on in during when stochastic process. But I just gave the proof for Borel-Cantor lemma. So there are two Borel-Cantor lemmas. One is Borel-Cantor lemma 1 and the other is Borel-Cantor lemma 2, which is also known as 0-1 law. So given a sequence of events, if you know that the sum of the probability of events is finite, then almost surely finitely many AIs only will occur. Almost surely means the probability of the event is 1. Finitely many AIs will occur means the event will only happen finitely many times. It will not happen infinitely many times. So after some point, the event will stop happening. Next, you have sequence of events and they're independent. And you know here the independent events is important. And then you know that the summation of probabilities is finite. Then almost surely infinite many events will occur. So what does this mean is that infinitely many number of times the event will occur. We did the proof for those, and that was the. So example for Borel-Cantor lemma coin toss was Suppose you toss coins infinite amount of times, and AI is an event where I toss is head. Now probability of an equal to 1 by n square. So as you toss multiple number of times, as n increases, so n is basically the number of times you've tossed the coin, the probability that you get a head decreases very rapidly. As you can see, it decreases by 1 by n squared times. So we know that the summation of 1 by n square is less than infinity. It is 6 by pi square or some term. Yeah. So what does this mean is only finitely many heads will occur. Intuitively, it makes sense because the probability of head occurring goes to zero as you increase the number of coin tosses. But the interesting part is, uh, if the probability of n was 1 by n, then we know that summation of 1 by n is equal to infinity. This, according to Polkadot lemma, says that infinitely many, no matter how many number of times you um, toss a coin, there'll always be a small probability, positive probability with which head will occur, and head will occur with probability 1. It's not just a small probability. It might take a long time, but infinitely many heads will occur. This intuitively doesn't make sense, but this is what the Burl-Cantor lemma law says, 0-1 law says, and we will see this why this happens later in the course. Okay. So next we spoke about random variable. So basically, random variable is also okay. So I'll start today's lecture because today's lecture again I'll start with random variables. Class 3, random variable. So every time you're given a stochastic process, you have a sample space, you have an event space, and you have a probability function. These three are given to you. Now, a random variable is a function which maps from the sample space to the real number line. It's just a function which maps the random variable from the sample space to a real number line, and this function needs to be f measurable. So what does f measurable mean? I'll not go too much into the mathematical writing of this, but what does it mean? So you have a sample space omega, and you have the real line r. So what x does is it takes a set and it maps it to some part of the real line. Now the inverse of this mapping back to here should be, it gives an event. The inverse mapping of the uh, x random variable gives an event. Now this event should be a part of the event space. If it is a part of event space, then it is a f measurable function. Okay, so let me give one example. Suppose your sample space is, you're tossing a coin, your sample space is head and tail, and you have made the event space as null set omega h t. This is your event space. And the probability measure is half comma half, like with half probability weighted and half probability weighted. Now, you can define a random variable which maps 1 if omega is equal to h, 0 if omega equal to t. This is a perfectly valid random variable. Okay, let me call this xh. One more function is equal to 0 if omega equal to tail, heads, and 1 if omega equal to tail. Any mapping is random. All these are random variables. Now, which random variable to choose depend given an sample space is, that is a decision that you need to make. So if you're if you're interested in knowing um, expected number of hits that happen when I do this for many number of times, then you choose a random variable such that you get 1 if omega equal to h and 0 if omega equal to tail. Then what happens is you are basically counting the number of times you're getting hit. Every time you get a hit, you add it to 1, you add it to 1, you add it to 1. If you're interested in the number of times that I get tails, then you choose this. If you're interested in something else, uh, the random variable, you can design it yourself, but make sure that it's a function. And one more thing is the function itself is not random. The function that the random variable takes an element from the sample space and spits out a real number. That is all deterministic. If if this is the outcome, it knows what it should map to. The mapping is all deterministic. There is no randomness. The only randomness in a random variable is comes from the sample space. Like once you do an experiment, you don't know what the outcome should be. But once you know the outcome, you know what the random variable value, real number value should be. So next, uh, now you know what a random variable is. So next is the distribution function. So distribution function fx is generally written as probability of x less than or equal to x, which is probability of x belongs to minus infinity comma x, where x is a real number. So what the distribution function does is it takes a real number and it tells, so if this is x, so what is the probability that it belongs to minus infinity comma x. This value is given by f of x. Mm, For one dimensional, we have f1 minus f of x as f of x. This will call as the cumulative CCDF, cumulative complementary cumulative distribution function. And f dash of x is equal to probability that x is greater than x. This is just the complement of this. So now um, x is a discrete random variable, which means that set of possible values is countable. So you have f of x. Oh, sorry. So x maps from the omega space to E, where E is a subset of R and E is a set of countable numbers. This is uh, a discrete random variable. The discrete random variable here, you no need to define the distribution function. You can just define the mass function. The probability mass function f x of x is given by probability of x equal to x. Okay, so let me give some examples for discrete random variable. So first we have Bernoulli random variable. So in the Bernoulli random variable, the set that you're interested in maps to is 0 and 1. Probability that the random variable is 0 is probability that x equal to 0 is p. This is also known as success probability. And p of x of 1 equal to 1 minus p. Or this this is 1 minus p. And 1, the event that you're interested in is p. Um, and this is known as success probability. Okay, so could you give some examples of like what a Bernoulli random variable in real life could be? So where you could model some process as a Bernoulli random variable. Okay, so coin tossing events can be modeled as a Bernoulli random variable. Next, we have uniform random variable on finite set. E is equal to E1 to En. We have probability of EI equal to 1 by n for all I belongs to 1 to n. Uh, so here the example was coin tossing. Here the example is this is a fair coin, die tossing, fair coin, fair die. Here the ED is 1 to 6 and probability of x equal to I equal to 6 for all 1 by 6 for all I belongs to 1 to 6. So the third one is binomial random variable. So you toss a coin n times independently with probability of success is p and x equal and the random variable is number of success in n trials. Probability that you see x number of successes when you do it n in n trials is equal to ncx p power x into 1 minus p power n minus x. Since this is the coefficient in a binomial expansion, this is known as a binomial random variable. And the binomial random variable, so if you toss a coin n number of times and you want to find what the probability of getting heads, say, how does the distribution look, then you can model using a binomial random variable. Okay, so the next discrete one is Poisson distribution, Poisson random variable. This has countably infinite uh, values that it can take, and the probability is given by e power minus lambda, lambda power x by x factorial, where lambda is the parameter that defines the Poisson distribution. Lambda is greater than 0. So there are a number of places where we model many things as Poisson random variable. This we'll talk about in when we talk about Poisson processes. So next is the continuous random variable. So a random variable x is said to be continuous random variable if there exists a function f small fx which maps from real numbers to 0 to infinity such that the distribution function of that can be defined by integrating it till x for all x belongs to real numbers. If you can get the cumulative distribution from this function which exists for the continuous random variable, this function is known as the probability density function. So for the continuous random variables, we'll be uh, giving the probability density function instead of the cumulative distribution function. And this is the cumulative distribution function, which we defined earlier. From this equation, we get that the derivative of the cumulative distribution function is the probability density function for all x. Um, okay, now some examples in continuous distribution. In continuous, we have uniform distribution. On the interval a comma b. So first we define the density function. The density function is given by 1 by b minus a if x belongs to a comma b, 0 elsewhere. 1 by b minus c. This is the density function. So the distribution function f of xx would be a, you integrate it from minus infinity to x. Let me write it down. Integrate from minus infinity to x fxx fxt dt. But as you can see that the density function is defined only from a, not elsewhere. So this is just integration a to x fxt dt. And in between a to x, you can see that this value is 1 by b minus a. So 1 by b minus a into x minus a for all x less than between a comma b, and um, it is 0 if x is less than a, and it is 1 if x is greater than b. So now you get the distribution function as follows. So a, b, this is 1, it's 0 till a, then it goes till highest till b, and then it's 1. This is effect distribution function. This is the density function of uniform distribution. This is the distribution. So the next one is exponential distribution. So exponential distribution, the density function is given by and the distribution function is given by you integrate it from minus infinity to x fx t dt. But since the exponential random variable is only defined uh, for positive x's, so this is basically integration 0 to x lambda e power minus lambda t dt, which is 1 minus e power minus lambda t, lambda x. So the density function is basically it uh, goes decrease exponentially. The rate at which it decreases depends on the parameter lambda. Yeah. So, but we have a nice property for exponential distribution, which is known as the memorylessness property. So the memoryless property uh, is basically used when you model waiting times. So when you're waiting for a bus or when you're waiting for a bus in a bus station, uh, it doesn't matter when the last bus came. If the buses are distributed, if the arrivals of the buses have an intra waiting time of exponential distribution, so the wait times are if they're modeled as an exponential distribution, then at any point you come, even that um, when the last bus has left, the probability that you wait remains the same. So what I mean is, so memoryless property of the exponential distribution. So probability of x greater than t plus s given x greater than s is equal to probability that x is greater than t. So here x is an exponential distributed random variable with parameter lambda. So what this says that given that you have waited till some time x greater than s, what is the probability that you'll wait t more seconds? It is the same as waiting t more seconds. It doesn't matter when you came to the bus stand. So what it says is, suppose a bus is arrived at 0 instant and bus left at 0 instant a bus stand, and the next bus will wait till an exponential random variable and then arrive. You don't know this time, this is random. Now suppose you have come uh, once 1 minute after the 0th bus has left. The probability that you'll wait 5 seconds or you'll wait for the 5 minutes is same as the probability if you would have come here and wait for the 5 minutes. It doesn't matter. It What has happened in the past doesn't matter. That is the specialty of an exponential distribution. This intuitively makes sense because you can see that the rate at which the rate is exponential, and so the probability remains the same. So this actually will be using when we talk of Poisson process, because in Poisson process, we'll see that the inter-arrival waiting times of their inter-arrival waiting times are exponentially distributed. So you wait an exponential amount of time before you get the next arrival when you model a process using Poisson distributions. So yeah, exponential distribution is going to come up again and again. So here I'll be doing the memoryless proof for exponential distribution, which we'll use later. Okay, so probability of x greater than s equal to 1 minus probability of x less than or equal to s. Now we know that this is the distribution function. And we know that x is exponential distribution with lambda. So this is 1 minus e power lambda s. This is taken from here. This is the distribution. Sorry. This is the distribution function for the lambda. This is equal to lambda minus s. Lambda for minus s. Okay. So now we calculate this term. So probability of x greater than t plus s given x greater than s is equal to probability of x greater than t plus s and x greater than s by probability of x greater than s. So this is condition probability. This is the conditional probability. Conditional probability of a given b, two events, is equal to probability of a intersection b by probability of b, given that probability of b is not equal to 0. If you know this, then this is how conditional probability is defined. Okay. So this is equal to probability that x is greater than t plus s, because so this is an event where x is greater than s. This is an event where x is greater than t plus s. You need the intersection of both the events. So if x is greater than t plus s, then obviously x is greater than s. But if x is greater than s, does not imply that x is greater than t plus s. So from this implication, what you get is x is greater than t plus s contains all the sample paths which has x is greater than s. So x is greater than t plus s is a bigger event. So if this is the event where x is greater than t plus s, then the event x is greater than s would always lie inside. Because if x is greater than t plus s, then x is obviously greater than s. So that event will be inside. And the intersection, oh, sorry, wait, this is, if x is greater than t plus s, then it will always imply x is greater than s. But there will be some events in x greater than s, which will not be in x greater than t plus s. So x greater than t plus s is a smaller event. And the intersection of those both would be the smaller one, which is probability of x greater than t plus s. The probability of x greater than s. Okay, if you have any doubts in how did I go from this step to this step, you can ask. So yeah, now it's just substitution of minus lambda t plus s by e power minus lambda s, which is equal to e power minus lambda t, which is equal to probability of x greater than t. So this is the memorylessness property of an exponential random variable. The third one is a random variable which you all know, which is Gaussian, or we call it normal distribution. So how are these parameterized? These are parameterized by mu mean and standard deviation or the variance sigma square is greater than 0. So this is mean, this is variance. Mhm. So the density function of a Gaussian random variable is given by 1 by root 2 pi sigma square e power minus x minus mu whole square by 2 sigma square for all x belongs to R. Hmm. So the distribution looks like this with mu as mean and sigma as the variance. It's yeah. I think you're familiar with uh, Gaussian distribution. Okay. So next we'll be going into joint distributions. So if you have two random variables, X and Y. Defined on the same space, same event space or the probability space. Then we have f of x comma y. This is joint distributions, which is written as probability of x less than or equal to x and y less than or equal to y. So from this, what we can see is fxx is the probability of x less than or equal to x and fyy. This is just the distribution of the random variable of x, distribution of random variable of y. Now we can get back these so these this is known as the joint distribution. Uh, these both are known as the marginal distributions. So you can get back the marginal distribution if you know the joint distribution. So how do you get back? So you look at this event. So you look at this event x less than or equal to x, y less than or equal to y. Now you suppose you want to get back the event marginal distribution of x. Then what you do is you consider a sequence yn, increasing sequence yn, which tends to infinity. So this sequence would be something like you have like 1, 2, 3, so on till it goes on till infinity. It could be anything. This is just one example of the sequence. And then what you do is you take the limit of n tends to infinity, x less than or equal to x, y less than or equals to yn. So, okay, so now we're talking about limit of sets. So now you have many sets. Now, my claim is that these sets are all increasing events. Okay, so why are these increasing events? So uh, let's take one by one. X less than, and let's take the example of yns are the sequence of natural numbers. So so okay, and y less than equal to yn, let this event be known as an. So now a1 would be x less than or equal to x, y less than or equal to 1. A, a2 would be x less than or equal to x, y less than or equal to 2. So um, y less than or equal to 2 event would have all the events in which y is less than or equal to 1. All the events in y is less than or equal to 1 would be in y is less than or equal to 2, because if y is less than or equal to 1, then y is less than or equal to 2. Yeah, so that is that point. So if x belongs to a1, then it implies that x belongs to a2, because what this says is y, the random variable, is less than or equal to 1. This implies that y, the random variable, is less than or equal to 2. So which implies that this belongs to a2. So all the outcomes that belongs to the event a1 would belong to a2. So this is your a1 and this is your a2, and it will keep on increasing. So you have an increasing, so these are all increasing sequence of sets. And from last class, we learned that the limit of an increasing sequence of sets is is the union of those sets equal to 1 to infinity, x less than or equal to x, y less than or equal to y. And now this union of these events is just x less than or equal to x. Now we take probability on both sides. So probability of limit n tends to infinity, x less than or equal to x, y less than or equal to yn, probability of x less than or equal to x. This limit n tends to infinity. This is from continuity of probability. You can exchange the limit and the probability. You get x less than or equal to x, y less than or equal to yn, into probability of x less than or equal to x. Sorry for this. No. So now this is limit y tends to infinity. So this n here symbolizes the um, that yn diverges. So you have a sequences which goes to infinity. The yn is a sequence which goes to infinity. So you can just create any sequence limit y tends to infinity f of x comma y is equal to fxx. So this is how you get back the marginal from the current distribution. And uh, independence. So yeah, I'm not independence. Yeah, I'm not going through this and giving more examples for this because it's just the introduction part of the course. And this is just a refresher of what probability, basic probability concepts. Once we'll get into the stochastic processes part, you will use this multiple number of times, so you'll get to know more about these things. So x and y are random variables and they are independent if the joint distribution productifies out with as a marginal distribution. So this is independence. And then you have expectation. Okay, so expectation of x is basically minus infinity to infinity x fx dx if x is continuous RV is summation x probability of x equal to x if x is discrete. Okay, next is variance. So variance of a random variable x equal to expectation of x minus expectation of x whole square. So you can expand this out. Huh. There are some properties of expectation. One of the properties is the linearity property, which will be used, and there is monotonicity property. It is similar to the probability law. Then there is Jensen's inequality. I'll tell about all the properties once I once we get to those stuff. So you can expand out the square. And here you use the linearity property. Here you use the linearity property. So what the linearity property of the expectation says that if you have two random variables, ax plus by, using linearity property, you can split the ax plus b expectation of y. Okay, so here what you get is expectation of x square plus expectation of x whole square minus 2 expectation of x. So this is expectation of x square plus expectation of x square minus 2 expectation of x whole square. Right, expectation of x square minus expectation of x whole square. So this is variance. Then you have covariance. So covariance of x comma y is defined as expectation of x minus expectation of x, y minus expectation of y. If you simplify this similar to what we did in the variance case, you'll get expectation of xy minus expectation of x expectation. These are the basic definitions for independence, expectation, variance, and covariance. So here we say that x and y are uncorrelated if covariance of x comma y equal to 0. And one important point to notice, uh, independence implies uncorrelated, but the vice versa is not true. Okay. Next is the conditional probability, which I defined earlier. So uh, where you have two events, A and B, such that probability of B is not equal to 0. Then you define probability measure A given B as probability of A intersection B by probability of B. It's the conditional probability. Then you have something called as conditional expectation. Okay, so conditional expectation, basically there are two types. So one is you condition on an event y is equal to y, and there is conditioning with respect to a random variable. So expectations, basically you take expectation of random variable. You don't take expectation of events. Probabilities are you take it on events, and expectation you take it on random variables. So conditioning, you can do either you do it on an event or you do it on a random variable. So if you do conditioning over an event, then this is a number, a real number. If you do it over a random variable, then this also is a random variable. Okay, I hope this the difference between two different types of conditional expectation is clear. So I'll mm, okay, so let's see. I'll explain this difference using an example. You can also solve the example parallelly, or you can give me inputs on how to solve. So let x and y are two random variables, which take values from 1 comma 2 and minus 1 comma 1 respectively. The joint PMFs are given as follows: x equal to 1, y equal to minus 1, equal to 1 by 5, x equal to 2, y equal to minus 1, equal to 1 by 5. Probability of x, y, x equal to 1, y equal to 1, equal to 1 by 3. Probability of x, y, x equal to 2, y equal to 1, 4 by 15. Okay. So now calculate expectation of x given y and expectation of y given x. So to do this, first we'll calculate conditional probability. Probability of x given y, x equal to 1, y equal to minus 1. Okay. What could this be? Okay. From the conditional probability, we know that this is xy, x equal to 1 and y equal to minus 1 by probability y equal to minus 1. So probability of x equal to 1 and y equal to minus 1 is 1 by 5. We know that from the question. Probability that y equal to minus 1 is just the sum of these two. So sum of these two, this is 2 by 5. So this is 1 by 2. Similarly, probability of x given y, x equal to 2 given y equal to minus 1. This is probability of x equal to 2 and y equal to minus 1 by probability of y equal to minus 1. So 2 and minus 1 is also 1 by 5, and minus half is half. So minus 1 is 2 by 5, so this is half. Similarly, probability of x given y, x equal to 2 and y equal to 1, equal to probability of xy 2 comma 1 by probability of y equal to 1, which is 4 by 15 by um, 9 by 15, which is 4 by 9. And probability of x given y, x equal to 1 given y equal to 1 is 1 comma 1 by probability of y equal to 1. 1 by 3 by 9 by 15. 5 by 9. So now first we'll calculate the expectation conditioning on the event y equal to minus 1. This is, so now x is a random variable. It will take values 1 or minus 1. So you sum over all the values that it will take. Sorry, x will take values 1 and 2. So you sum over all the values. So 1 into probability that x equal to 1 given y equal to minus 1. So this is probability of x equal to 1 given y equal to minus 1 plus 2 into probability of x equal to 2 given y equal to minus 2. This we have calculated above. This is 1 by 2 and this also, sorry, y equal to minus 1. This also 1 by 2. So this is 1 into 1 by 2 plus 2 into 1 by 2. This is equal to 3 by 2. So as you see, if you condition a random variable over an event, you get a number. Now expectation of x given y equal to 1 is 1 into probability of x given y, x equal to 1 given y equal to 1 plus 2 into probability of x equal to 2 given y equal to 1. And this is 1 into 5 by 9 plus 2 into 4 by 9, which is equal to 13 by 9. Again, this is a number. Now, you want to find what expectation of x given y is. Expectation of x given y is basically expectation of x given y equal to minus 1 with probability y equal to probability that y equal to minus 1 and expectation of x given y equal to 1 with probability y equal to 1. So expectation of x, if you know that y equal to minus 1, then that is 3 by 2. If you know that y equal to 1, then that is 13 by 9. But since y itself is random, you don't know which will occur. So expectation of x given y, when you're conditioning on a random variable, this will be 3 by 2 with probability y equal to -1 is 2 by 5. 2 by 5. And 13 by 9 with probability 3 by 5. So this itself is a random variable because you have uh, uh, so you have real numbers and you have probabilities associated with the real numbers, the PMF. This is how the random variable is the discrete random variable. So I hope this is clear. If you have any doubts, you can ask it. So next we'll go into concentration inequalities.
Yeah, it's clear.
It's clear. Okay, fine. Concentration inequalities. Okay. Yeah, so the first concentration inequality is Markov inequality. Okay, so for x non-negative random variable, we have the Markov inequality as x greater than or equal to epsilon is less than or equal to expectation of x by epsilon. This is for all epsilon greater than 0. Okay, so how do you show this is expectation of x equal to expectation of x into indicator x less than or equal to epsilon plus expectation of x into indicator x greater than epsilon. Okay, so let me first describe what an indicator function is. So an indicator function. So if I have, okay, let's do this. So indicator of a omega, which is a random variable. So this is 1 if omega belongs to a, 0 if omega uh, do, does not belong to a. So what it does partitions the um, the whole sample space into the event that you're interested in, the event that you're not interested in. If you get an outcome in which the event is there, then you get a 1. If you get an outcome where the event is not there, then you get a 0. So now here what I've done is x is a non-negative RV. So x can take values from 0 to infinity. So now I've taken some epsilon greater than 0, which will lie between 0 and infinity. So I've partitioned this in as the random variable x will lie either in this part or in this part. So either this will be 1. If this is 1, then this indicator will be 0. If this is 0, then this indicator will be 1. But it doesn't matter because x can't be there at both the same time. It will be at only one place. And once it is 1, it is just the expectation of x, if you know where it is. So expectation of x can be written as expectation of x into indicator. Now the event is the random variable x is less than epsilon. And here the indicator is random variable x is greater than epsilon. So I've partitioned the whole real line. Okay. So I hope this is clear. Next, what I'll do is, since x is a non-negative uh, random variable and indicator is 1 or indicator also is positive, it's either 1 or 0. So expectation of all positive numbers will always be positive. You can't get a negative number if you have all positive expectation. So this expectation will always be greater than 0 or greater than or equal to 0 if it could be 0. So this is less than or equal to expectation x into indicator x greater than epsilon. So what I'm doing here is I'm removing a positive term from the summation. If I remove the positive term, the left-hand side value will decrease. So I just remain with this. Now what I do is when this indicator is 1, I know that x is always greater than or equal to epsilon. So I can again decrease this with replacing this with epsilon into indicator x greater than epsilon. So now this would generally be a sum of all the values that x can take. But I know that x is always greater than epsilon. So I replace all the x's with epsilons. And I know that the sum would be less than what the original sum is. So this is equal to epsilon into expectation of indicator x greater than epsilon. Now indicator, I have defined what the random variable is. So this is equal to epsilon into 1 plus probability that x greater than epsilon, sorry, 1 into probability that plus 0 into probability that x is less than or equal to epsilon. This is equal to epsilon into probability that x is greater than epsilon. Maybe here I've taken this wrong. This is x. It's a minor mistake. X greater than equal to 81 less than greater than 48. So now you have expectation of x by epsilon greater than or equal to probability of x. Okay, so I'll write it in the reverse. So it is. So you have probability of x greater than or equal to epsilon is less than or equal to expectation of x by epsilon. This is the Markov inequality. And this is very important inequality, but this doesn't has many practical use. So I'll give you an example why this doesn't has much practical use. Because so suppose you have a density function, you have some density function, and you have the mean where you have expectation of x. Now, okay, suppose you have an epsilon 1 on the left hand side of the expectation. So you know that expectation of x is greater than. So what is the probability that x greater than or equal to epsilon 1? So this probability is basically this curve, this part, right? Okay, so this is the Markov inequality saying that this is less than or equal to expectation of x by epsilon 1, right? But you know that expectation of x is greater than epsilon 1, which implies expectation of x by epsilon 1 is greater than or equal to 1. So you're saying that probability of x greater than epsilon 1 is less than or equal to something which is greater than 1. So here you have a, this a is greater than 1. Probability of any event is less than 1. So this inequality is like redundant. You gain no extra information from the Markov inequality. Okay, I hope you understood where Markov inequality does not work. Okay, I'll give you an example where Markov inequalities work. So suppose you have a density function and so you have expectation of x. Now suppose I take the tail thing as x expectation. So now what you want to find is probability of x greater than or equal to epsilon 2. Now this epsilon 2 is the area here. So according to Markov inequality, this gives you less bound on expectation of x by epsilon 2. And now since you know that epsilon 2 is greater than expectation of 1, this is something which is less than or equal to 1. And you get this as a number, and you can lower upper bound the probability that you find here. So so the Markov inequalities are useful in these kind of cases, and Markov inequality doesn't give you extra information when you uh, in these type of cases. So no extra information here, no extra information. useful. Next is Chebyshev inequality. So X is a random variable. Now you don't have the non-negative X. Markov only work with non-negative random variables. X would be here, X would be any random variable. Then you can say that X minus expectation of X whole square. This also is a random variable. And this is a non-negative random variable. Now what the Chebyshev inequality says is X minus mu greater than C is less than or equal to sigma square by C square. You basically derive this by applying Markov on this. The other statement that Chebyshev makes is probability of X minus mu greater than K sigma is less than or equal to 1 by K square. It's just replacing C with K sigma, you get this. So these both are the Chebyshev inequality. So what the Chebyshev inequality tells is, so you have density function of X and you have some mean. So so this is your Chebyshev inequality. So what this implies is the probability that X is greater than or equal to expectation of X. So here mu is the expectation of X plus K epsilon, or X is less than or equal to expectation of X minus K epsilon is less than or equal to 1 by K square. So here you have somewhere expectation of X minus K epsilon, K sigma, sorry, K sigma, and expectation of X plus K sigma. So what the Chernoff bound gives is the probability that you are either lower than this or more than this. So basically the tail probabilities. So Chebyshev inequality gives you an uh, uh, upper bound on the tail probabilities. Like what is the probability you'll be at the tail end of both the distributions. Okay, so I'll give an example where Markov inequality. And then okay, I'll give an example for Markov inequality. So you have a biased coin with probability of getting a head as 1 by 10. So the probability of getting a tail is 9 by 10. It is flipped 200 times. And okay, so give an upper bound on the probability that it lands head at least 120 times. So here we'll be first defining a random variable xi. So let the xi be the random variable. Is a random variable which says which is equal to 1 if outcome is head at the ith toss, is equal to 0 if otherwise. So this is the random variable. Now we are counting the number of heads that we have seen in 200 tosses. So I equal to 1 to 200 xi. So what will this do is it will count the number of, this is the number of heads seen in 200 tosses. Okay, so expectation of S is expectation of summation I equal to 1 to 200 xi, which is equal to summation I equal to 1 to 200 expectation of xi. Expectation of xi is nothing but 1 by 10 because it's 1 into probability of head plus 0 into probability of tail. 1 into 1 by 10 plus 0 into 9 by 10, which gives you 1 by 10. So this is summation I equal to 1 to 200, 1 by 10, which is 200 times 1 by 10, 20. So the expected number of head you see in the 200 tosses is 20. Is clear. Now, what the question is asked for, the number of times you see head is at least 120 times. So probability of S is at least 120 times is that the event that S is greater than 120. So you can see something which is more than 180, but you must see at least 120 heads. So that is the event. So this from the Markov inequality, we can say that this is less than or equal to expectation of uh, S by 120, which is equal to 20 by 120 equal to 1 by 6. So an upper bound on the uh, probability that it lands at least 120 times is 1 by 6. This is how you use Markov inequalities to get upper bounds and probabilities. This we'll see more later also. So yeah. So I'll stop the class today. Next class also, I think I'll continue with uh, introduction. Next class, I think we'll talk about convergence of random variables
Okay.
and convergence of random variables and limit theorems, central limit theorems. So limit theorems. After that, we'll go into Poisson process, Poisson processes, then renewal process, and then uh, Markov chains.
Okay.
Yeah,
Okay. Thank you, Ankit.
yeah. You